Hello everybody, welcome back to Human Resource Machine. Last time we were working on level 38 Digit Exploder where we completed the size challenge, but we still needed to work on the speed, so let's get to it. Today I came back with a few different ideas that I want to try out, which hopefully will get us past this challenge. The first idea I had is when we subtract 110 to get our count of digits, we always subtract them one at a time. But if you meet a large number like 73, then when you subtract 10, you have to subtract it 7 times, which obviously takes a lot of steps because you have to go through the iteration 7 times. And it could apply to a higher number of hundreds too. If you have like 999, that's a lot of iterations to go through. So what if we reduce the number of iterations that we have to go through? So the way I'm going to do that is I'll copy from 100, I'll add another 100 to it, and I'll put this over here, let's say. So this is going to hold a value of 200. And then I'm going to do the same thing with 10. So that this cell has the value 20. And these are constant numbers. And when I start subtracting, I can copy this loop, make a copy of this. So that'll be copy from 0, sub, and this time instead of subtracting 100, I'm going to subtract 200 at a time. And we have a jump if negative. We have a copy 2 and a bump, except this is our count of hundreds. So instead of bumping it once, we're going to bump it twice to say that we have subtracted 200 from the number. And then jump back to the beginning. This is our loop where we subtract 200 at a time. And so this loop should execute half as many times as our original 100 loop. After that, we still need to test if there is a single 100 remaining. So everything else is the same, I think, except we don't need this jump anymore, because all we're doing is, well, after this loop, the number has to be between 0 and 199, so it's not possible for there to be multiple hundreds remaining after this. The rest of this should be the same. I'm going to do the same thing here for the number of tens. So copy, subtract. This time I'm going to subtract 20. Jump. Copy to 0 is correct. And this time bump up 7 twice. And jump back to the beginning. Here again, there can only be at most 110 remaining, so we don't need this loop anymore. Alright, that was our first idea. This deals with big numbers with high digits. Now there is another thing where if we have a number like 2, then we don't want to spend all our time testing, can we subtract 200? No. Can we subtract 100? No. Can we subtract 20? No. Can we subtract 10? No. All of that is very much pointless work. So let me do a little test up front. So get the inbox, we get our number. Let us subtract 10 immediately and test if it's a number that's less than 10. That means it's a single digit number. And if it is, then we just skip all this stuff and we can jump directly to here and output our single digit. So we skip a lot of work in between. And similarly for the number of hundreds, let's get our number back, subtract 100. So we've tested it's not less than 10 now. We know it's a 2-digit number. Let's test if it's a 3-digit number. And if it is not a 3-digit number, then we can skip this loop where we subtract by 200 at a time, we can skip the logic where we subtract by 100 at a time and just start by testing the number of tens immediately. That should be another way to skip a lot of instructions if it's only a 2-digit number. Alright, with that, let's test it and see how fast it is. Hmm, 181. It's much better than before. I think before we had like 200 something, so it's a big improvement, but still not quite there. Alright, I wonder if we can make it even faster. So instead of 200, let's add another copy of this. Let's make this 300. And then similarly for the tens, let's make this, let's make this 30. And then instead of bumping twice, we're gonna have to bump 3 times. Same thing here. And this time we do need to reintroduce this loop, because after subtracting by 300, it's possible that we need to do the 100 loop twice. Same thing for the tens. Let's see if this will go any faster. Okay, no, that's even slower than before. Before we had 181, but now it's 184. So yeah, I think we're just testing too many conditions, and if it's in the number of hundreds, then we have to do 2 loops now, which is probably not the most efficient thing. Okay, so let me think about it some more. I've restored the program back to the way it was before we started trying that idea, and I want to try a different approach. So the thing I want to work on now is this copy from and copy to. So you can see every iteration of the loop where we subtract 100 at a time, we have to do 2 copies to save and restore the value. And then every iteration of the loop where we subtract 10, we also do this copy. And the only reason we have to do that is because we need to bump our count of how many times we've subtracted. And because bump modifies the value in our hand, this is why we have to save and restore the value every single time. What if we did this bump separately so that we didn't have to copy to and from every single time? So I'm still going to start with the value. This is our initial value. Let's subtract 11. Subtract 100. If it is negative, that means we don't have any more hundreds to subtract. And so this is fine, we're going to leave that. But right after this, if it is not negative, that means we've already subtracted 1 time 100. Let's just subtract another 100 and see if that's negative again. If this is negative, that means we've subtracted 100. So we need to maintain a count of 1. So we need to bump up this value by 1. But before that, let's add 100 to our value and then save it to 0. So instead of saving the value immediately over here, we wait until we've done all our subtraction, then we get down to here, restore the value so we make sure it's positive, and then we save the value only once, and then we bump the number. We can keep doing this. We can subtract another one. So here, if assuming it never became negative, we can subtract 3 times in a row. If this is negative now, This is the case where we've successfully subtracted 200. So the number is between 200 and 299, essentially. The leading digit is 2. And we're going to do the same thing, add 11, copy to 0 so that we save the result. But in this case, we'll bump up 8 twice. And I'll just do this one more time. Jump if negative. Right here, we still want to do the same thing. And then in this case, I will bump 8 up 3 times because we have subtracted 100 3 times. The 4th time is to tell that the number is now less than 100, so we added 100 back. We don't bump 8 by 4 times. And after we do this, we get to the end of our loop. Let's do this here as well. Go to the end, and here go to the end. So now at the end, I could keep going and do like all 10 possible values, subtract 10 times and fill in all this, but that gets extremely repetitive and extremely long. So I'm gonna take a little shortcut and let's see. Yeah, if by the time we subtract it 4 times and it's still not negative, I'm gonna just bring it back to, actually, and it's still not negative. That means we need to keep count. Bump 8 up 4 times. Oops. Before that, I also want to save the value. Bump 8 up 4 times and then repeat the loop again. So now we have another chance to subtract another 4 times 100. And each time, depending on how many we've subtracted, we will bump up 8 by the corresponding number of times. And the important thing is for each of these loops, we only need to copy from and copy to once. So we save many steps that way. In the end, once we get our hundreds, the output stuff is still the same. And so now I'm just going to do the same thing to the tens. I've done exactly the same thing as above. So here is what we did for the hundreds. We have each iteration of the loop, we have a chance to subtract by 400 up to 400, and we bump by the corresponding number of times. And here we're subtracting 10 at a time. We have a chance to subtract up to 4 times 10 per loop, and bumping up the correct count in this case. And down here we still have the same output logic. Oh yeah, for the outputs, since we have the count stored, we don't have to output everything here. So I don't need to copy from 8 and worry about outputting the number of hundreds right now just yet. We can save a few steps by doing this. Right now we have the count of hundreds. If it is 0, then we start testing the number of tens, and that logic is still good. But if it is not 0, then we can outbox the number of hundreds and jump to our count of tens. This way, I think we're going to save a couple of steps as well. Let's try this. How's the speed? 169. We're almost there. We're just 4 steps down. Oops. Let me redo that. Alright, so I think the basic concept has proven itself. this one reduced our number of steps to almost a challenge. So let me just add one more layer of this loop. So basically sub 11, jump if negative, and that's another layer. We have to bump this one more time in that case. You know the drill. $166, really? Really? Okay, one more. One more. Okay. Alright, we finally got there. Yeah, this is a really stupid solution. Like, I'm pretty sure they don't expect you to write something this repetitive. Like, yeah, but I'm totally out of ideas. I've been working on this for a while now, and I just don't have any better ways of doing this. So I will continue thinking about it. If I find any better ways, I will come back to this and do that. But right now, I guess I'll have to leave it here because this is the best I've got for now. Alright, let's go to next level 39, Recoordinator. Pawn to b6, and check, and mate. Yes, I win again. I find the game is most enjoyable when playing against the best player I know, myself. Alright, each number in the inbox is an address of a tile on the floor. Send to the outbox the coordinates of that tile, column first, row second. For example, an address of 6 has coordinates 2, 1. Okay, 2, 1. You may ask your boss for more examples. Alright, so yeah, this is another division. So you take the number, divide it by 4, and then 2 is the remainder, 1 is the quotient. So it's basically like the number exploder, whatever it was called, level that we just did, except it's in base 4 instead of base 10. So I'm just gonna unroll the loop immediately because there are literally 4 possibilities. So I can just do that. Okay, inbox, we already have the number 4, that's good. It wants, oh yeah, it wants a column first, which is odd because the column is the remainder. Normally, if I were to do this, I would output the row first, because row is like the higher order, the higher digit in base 4 when you write it in base 4. But whatever, they want it in reverse order, that's fine. Get the inbox. Subtract 4. If the result is negative, we know the answer is somewhere between 0 and 3, so let's add back our 4, and then just copy that, and then just send that to the outbox. This is our column, and then they also want the row. The row is going to be 0. So I will copy from this and send that to the outbox. Actually, let me make a copy of that. Copy from this, copy to here. And so this will be a constant 0. I'm not going to touch that. This is going to be the one where I count the number of times I've subtracted. Okay, so this is the case where the number's between 0 and 3. Now, if it's not, then let me subtract again. And now it's going to be somewhere between 4 and 7. I'm going to do the same thing, add 4 back, send that to the outbox. And this time I'm going to bump 13 up and by 1 and send that to the outbox. And go back to the beginning. Next case, subtract 4 again. This time it's going to be between 8 and 11. Jump if negative. Add our stuff. This is still to the outbox immediately. This is our remainder. Now I'm going to bump up twice and send to the outbox. Repeat. And finally, if it's still not negative, then it's between 12 and 15. So we don't need to subtract again. We don't need to add again. We can just send that directly to the outbox. Bump this up 3 times. And out. Alright, hopefully this will meet the speed challenge. Okay. For some reason this did super good on the speed challenge. I hope for the other one I didn't have to literally write out all 10 possibilities, because that would be ridiculous. Alright, let's work on the size. The size, we just need to roll up the loop. So yeah, I'm not gonna clean this up. Let's start a new one. Alright, let's get our number from the inbox. And then here we're gonna store our quotient. Here we're going to store our remainder. Inbox, let's copy that to the remainder. And for each iteration of our loop, a copy from the remainder. This is a loop where we do the subtraction. Subtract 4. If the result is negative, we know that our remainder is already less than 4, so we output the copy from, we output the remainder first, because that's what it wanted. Copy from our quotient and outbox that, and jump back to the inbox. Now we do need to keep track. So if it is not negative, we want to copy the remainder. So update our remainder, but also update our quotient, and this jump should go here. This is basically what we did for the digit exploder. Yeah. Yes, I did not initialize the quotient. I also did, yeah. Copy from 0 and put that in the quotient initially. I expected 1, but I output. Really? When was that? Oh, right. Because I need to copy from remainder, either that or add 4 back, because, yeah. We need to save one more instruction. Okay, let me think about that. Alright, this was a little hard to find, but in the end it was pretty much the only logical possibility. Everything else is pretty much essential. The only thing that caught my eye is these 2 copy to instructions. This is a duplicate, and when there's a duplicate, there's usually a way to remove it. So the reason we had copy to and copy from here is because we're bumping up Q in the middle. And whenever we bump Q, we need to save and restore the value. Since we have copy to and copy from here, why not put this loop above the copy to, put the bump in between here, and get rid of the duplicate instruction. That lets us get rid of one instruction, but now our output is going to be messed up because we've bumped Q one extra time, and so we'd have to bump down Q, right? Luckily, bumping Q also puts that value in our hand, so we don't actually need to copy from Q anymore. I think this will get us the right result in the end. So in terms of Q, we bump it up an extra time even before we subtract. So if when we subtract and it happened to be negative, then our Q should not be 1, it should be 1 less, but we are also bumping it down here. So that's the correct result. And R, we get the inbox, immediately copy it to R and copy it from R. We still do the subtraction correctly. And if it's negative, we get the previous value before subtraction from R. So that also gives us the right value. All right, done. Next, number 40 is prime factory. Are you sure you're supposed to be here? This is a very difficult assignment. I have no idea how to do it either. For each thing in the inbox, send its prime factors to the outbox in order from smallest to largest. Alright, yeah, I've done this before in a different language, but sure. So the idea is, let's make a copy of that and bump this up to 2 initially. This is our, let's say, divisor. So so in the beginning, we want to take our inbox, copy that to, this is our in number. What we're going to do is take our in, divide it by 2, and look at the remainder. If the remainder is 0, then it is divisible by 2, so we output a 2. And then we keep doing that until we can't divide by 2 anymore. Next, we bump up the divisor, so now it becomes a 3. Do the same thing, divide whatever remains in by 3, and if that result is the remainder is 0, then we output a 3, because 3 is another prime factor, and then repeat. We keep increasing the divisor, keep dividing by the divisor. That's how it's going to work. So we got our in, we got our divisors, so let's divide. So we don't want to destroy our in value. Actually, we don't need to keep track of the quotient. No, we do need to keep track of the quotient. Alright, let's do our regular division loop. Let's make, no, copy from in, copy to another value. This is our working number. I don't know what to call it. Copy to and copy from is necessary because I'm gonna put a loop here eventually. Now we're gonna start dividing work by divisor. Let's subtract our divisor. If it's negative, then copy the, okay, no. If it's negative, then we're done subtracting. Yeah. If it's not negative, then we have more work to do. So we bump up the quotient. So let's call this quotient. Actually, instead of work, I'm going to call it remainder, because that's what it is. Copy to remainder, bump up the quotient. Copy from remainder again, and jump back up to here. So we have our remainder set up. This is the division loop where we keep subtracting the divisor, and if we have more, then we update the remainder and quotient and do it again, subtract again. If it's now negative, which means we can't subtract anymore, we have the remainder and we have the correct quotient. So now we need to check, get our value from the remainder. If the remainder is 0, that means we have found a prime factor. I guess we'll just get our divisor, send that to the outbox, and then we go back to, no, not yet. We get our divisor, send it to the outbox, get our quotient, and this is our new in number. So we've successfully divided in by the divisor, so now we're updating the in to be whatever number remains after dividing, and that would be the quotient that we got from above. So copy 2 in, and then I guess we don't need to copy from after all. Yeah, we do need to copy 2 in, but if we just do this, we can remove that instruction too. This is the case where we found a prime divisor. If we did not find a prime divisor, that is, if the remainder is not 0, then we'd want to bump up the divisor and jump to here, where we start dividing again, except we need the input in our hands. Copy from in. When we get here, the in is going to get copied to the remainder, which resets the rest of the calculation. Yeah, I feel like I'm definitely missing something, but this is all I can think of for now. So let's try it and see what breaks. Empty value, you can't bump. Oh, I just didn't set up the queue. So let's copy from 24. Okay, we already did that. Copy to divisor, but we also want to copy to the quotient, because quotient we never initialize it, we just bump it up all the time. And here's something else I forgot. Oh, yes. After we divide everything, eventually in is going to be 1. And so where is the case where we've found a prime divisor. Yeah, and we go back to the beginning. So now we have our input, but we want to test our input against the divisor. And if it's negative, that means our divisor is now bigger than the input, which means we definitely cannot divide anymore. And this is the time to reset everything and work on the next input. And of course, after we do that, we want to restore our input so that we can continue the loop and do everything else. Let's try that. Let's go back and see what we were doing wrong. Oh, it's because I never reset the divisor. So I finished processing the previous number, but then the divisor has already been incremented to 3, and I never reset it. That's weird. I should have reset it. Yeah. I should have been coming in here. Copy from 24. 24 is 0. 0, copy 2, and it should... I don't understand. When was the other point where we got another input? We could not have gotten another input without resetting. I probably did the division wrong then. I'm gonna have to debug that again. Okay, so now divisor is 3, input is 9, so it should output a 3. And something is horribly wrong with the input. Yeah, I should have another 3. I don't know how 7 got in here. Somehow it thinks the quotient is 7. Maybe because I did not reset the quotient after dividing the first time. Yeah. I did not reset the quotient and remainder when division failed. This branch is when the division failed. Wait, jump if 0. Yes. So here's where we got the final remainder. If the final remainder is 0, then this is a prime factor. We got that side handled. If it's not a prime factor, then we bump up the divisor. We also need to reset the quotient. So let's copy from 0 and put that in our quotient, because yeah, resetting quotient, this is the only place where we should reset the quotient, and so we need to also reset it in this branch over here before we get the input. Alright, there are some inputs that cause my program to fail, so let's look at those. 4, 10, and 3, let's run it and see what fails. Yes, I see quotient not being reset again for some reason. Oh, I think I know. In this case, in our successful division case, the quotient is not being reset again. Let's see, where do we jump here? Right after inbox. Where do we jump here? Okay, this is our division loop. So maybe before we divide, yeah, every time we divide, let's copy from 0 and reset our quotient. And now we need to copy from in so that we don't have to reset the quotient here because we are resetting it before using it. And we don't have to reset the quotient here either because this jump will jump over here where we do reset it. And we don't have to reset it here because it'll jump over here and eventually get down here where we reset it. So that should get us correct resetting of all the quotients in all the cases. Yay, I just hope I don't have to optimize this beast. Alright, size, good. Speed, need quite a bit of work. Alright, I think this episode is long enough. I will come back next time to optimize the speed, So that's it for today. Thanks for watching. See you next time.